Alright, in the last video we discussed about feature engineering and we created a set of features. Now in this video we are going to discuss about something known as train and evaluation spec that is going to help us to scale the model in the future videos. So let's take the first step today. This is normalization. Let's look at the data set. So after adding the features like pick up lat, pick up lon, drop off lat, drop off lon, longitude diffs and latitude difference and the Euclidean distance, we are with these features. Now we will do normalization. The reason we want to do normalization is because look at the value of trip miles. It is like 14 miles, 20 miles, 5 miles, 1 mile versus trip seconds, which is in hundreds and thousands, right? And then pickup latitude, longitude is in hundreds, like 42 and 87, and then these are like less than 1. So now it's very uneven, the scale of these numbers, because it's all about maths, right? This is TensorFlow and neural network is nothing but all mathematical numeric calculations, and therefore we need to do normalization. What is normalization? It's a technique which is applied as part of data preparation for machine learning. Normally, the goal of this process is to change the values of this numeric columns to a common scale. We want to ensure that there is no distortion of the differences in the range of values, and that is why we do normalization. So what we will do is we will take the entire data set and normalize it to a value which are equivalent in scale, but the range, the meaning of that data set would still remain the same. Let's see how we do the normalization. So this is how you would normalize a data set. I have written a function which is normalize data set, and then we are gonna do data set minus minimum divided by data set max and min, the difference of between max and min multiplied by 20. So we are going to do this normalization so that the scale is between 0 and 20, and that is why you would see all these values changed. But please understand that this is all to make sure. There are two benefits of standardization. The first is it provides common scale of value, and the second is it helps to train the model faster. And because it's a linear regression, ultimately, beneath the words, it's all dependent on how one particular, let's for example, the number of the value of trips is in thousands and this is in hundreds. Sometimes the trip seconds would overweigh the impact of pickup latitude, and that is why we want to make sure that all the values are at the same scale. Next step is train and eval spec. This is required, and this is a little bit different, but it's almost the same as what we did in the previous videos. So let's understand this also. Here I am doing some run config. That means remember the checkpoints which we discussed in the previous videos. So after 30 seconds do a save checkpoints, and maximum number of checkpoints I'm going to keep it as 3. I don't want to have more than 3 checkpoints kept because unnecessarily it's going to take my space. Next I have DNN linear combined regressor. Please understand that during the feature engineering we defined the wide columns and the deep columns. The wide columns meaning the sparsely populated columns, and deep column meaning densely populated columns. So when I say DNN linear combined regressor, that means the wide column which are sparsely populated will go through the linear regression path, and the columns which are deep columns would go through the neural net path. So this is the meaning. Don't get too much into detail. You can read or Google it. But for now, just imagine that it's a combination of deep neural network, which is DNN, and the linear regression, which is very typical. And you got the best of the worlds. In the previous attempt to find out RMSE, we just did DNN, which is deep neural net. But here we are doing a combination of linear because the sparsely populated columns, that is wide columns, may not work well or will not work well with the deep neural nets, and that is why we had to do this. Again, so linear feature columns is wide columns and deep neural net feature columns is deep columns. This is how you enhance the performance of the model, best of both worlds. And you can see I increased the DNN hidden units to 128, 64 and 2. Earlier we had 64, 32 and 2. It may not directly affect all the time, but it does more often than not. So I defined a DNN linear combination model. Please remember, it is build the graph, train and test. So this is the building. Now this is the feature function, the input. Remember the make input function. Now I'm calling this as feature input function. So this is going to be used in train and eval spec later. So very simple, the same, exactly the same. This you must have seen before, the make input function. X is going to be X, Y is going to be Y, and then batch size is 128, number of epochs is whatever you pass, the number of epochs. Shuffle true, the last time I had shuffle false, and then number of threads 1. It does not change anything over here. This all is same, just I am renaming this function as feature just to make it that differentiation. Next is the train and eval spec. In the last one, in the previous one, what we did was we used model.evaluate and model.train. Here we are going to do a little bit different. So this is a train spec, which is an tf.estimator.train spec, tcaps, scaps, and all I am doing is calling the feature input function with the x train and y train with number of epochs as 100. And then eval spec, which is model.train and model.evaluate. Eval spec, I'm calling tf.estimator.eval spec. Again, the same function, exactly the same. And then throttle seconds is 10. It does not change anything. I'll repeat one more time. I'm calling this feature input function for eval spec and train spec exactly the same as I did earlier, no change. And finally, here, based on the estimator, which is the DNN linear combined regressor, train and underscore spec is the train spec which we created, and eval spec which we created. We are passing this through a tf.estimator.train and evaluate. So if you pass the train and eval spec, this estimator function is going to give you a combined output. And at the end of it, we are calculating the RMSE. So we are going to look at the hands-on DIY, and you would be surprised with the RMSE we got using the feature engineering and normalization. Let's look at the code. A quick recap of the code. So here we defined the feature engineering columns. I have this video which you can take a look. So this is feature engineering columns. We defined wide and deep columns. Next, we created this data frame out of exactly the same columns as we used without feature engineering earlier. And then I created this add more feature columns, in which in the last video I created the Euclidean distance. From here on, this is we haven't seen yet. So this is the renaming of the columns of the data frame, which we have done earlier as well. And then I called add more features so that you can see I added long, lat diff and Euclidean. Now I'm gonna write this normalize function as discussed. This is gonna normalize to the scale of 20, and then I call this function normalize here to normalize, and you can see the difference between these two values. Next, the same train test split. Here I'm calling the feature x train and feature x test, feature y train and feature y test. The same, the number of records is the same. I'm just scrolling up a little bit, and you can see that this section, I'm scrolling up, training a different linear model. In the prepare section, you would see exactly the same. I am taking the number of columns. So please understand that there is no difference between the number of columns, exactly the same. Our target is to beat the RMSE score of 14.83. In fact, not just beat it, but enhance it to a very, very high level. So let's go down here, here, and this is where we did a train and test split. So nothing changed here. Now in this one, as we discussed, we will define a run config, and then we have DNN linear combined regressor with out directory and linear feature columns, wide columns and deep columns. And again, just to keep it very same as the previous one, I kept it as 64, 32 and 2. Otherwise there would be a question that, hey, why did you change the units and all? So just to be safe, that hey, I'm using the same kind of neural net model but with feature engineered data and normalized data, and you can see in a short while what would change. Next, I define this feature input. Again, this remains exactly same. I have not changed anything. It remains the same as in previous. I have created a train spec and eval spec, and train eval spec is a TensorFlow estimator function. It is used in future. I'll show you to scale the model up. So I'm gonna reach there, but for now, very simple train spec and eval spec with feature x train, feature y train, and number of epochs for training 100, exactly the same as the previous one. And when I run it, I'll pause the video. Okay, so I ran it, and you would see here that estimator.train.eval, estimator, train spec and eval spec. When I call this estimator function for this yellow caps, exactly similar to the previous one, I saw the RMSE, the loss to be decreased, I mean to be down at 27. And when we calculate the RMSE, very similar form of calculation, nothing changed here. The RMSE was 5.22. So think of an RMSE, I'll just scroll up one more time. Think of an RMSE of the previous one as 14.83 versus an RMSE now as 5.22 with the exactly same number of epochs, batch, everything remains the same. All I did was did the feature engineering and bucketing. That's how you can change the prediction. So that means now the model is able to predict within up to $5 variation. So if you have a $30 trip, the model can predict $25 to $35 range on an average. Isn't it great? So you can see how a feature engineering can change what your model can predict. So we'll take this 5, and this is the RMSE to beat. Do more feature engineering, and that is your next hands-on. So hands-on is make a copy of this Python notebook, TensorFlow feature engineering for a DNN model, and then implement feature engineering as discussed. Just implement it, go through the code a little bit more, and then track your changes of the parameter. Let's beat this RMSE by changing these parameters. I'm sure you can beat it. I think in one of those attempts I went down to like 4.12 or something, so you can still beat this RMSE. I don't want an RMSE like 0, because that means you're predicting 100% accuracy. That's not going to happen. So a typical RMSE for this particular example, because RMSE can change depending upon what you're trying to predict, but RMSE for this particular example, I would like it to be within $4. So let's see if you can do that. And then finally, questions to ponder over. What other potential feature engineering options you can think of? There is a video out there which I have put on different types of feature engineering. So look at that video. The link is in the description section of the video below. And then post your answers on this Facebook group. So this Facebook group is also mentioned in the video description section of the below. Go join this Facebook group. It's a great site for all TensorFlow related and other machine learning related stuffs. In the next set of videos, we are going to talk about how to save this model and publish it on a Google Cloud platform for scaling it up, to a level wherein you can start putting this model online so that people can start using this for prediction. And that is how you productionize that model. Hope this was good. I know it's a little bit challenging to understand everything. You need a lots of hands-on, and that is why hands-on DIY number 5. Thank you for watching.